Talk about ratios and proportions and how those things apply to geometry. So this is the review of the whole similarity unit. So we're going to go through them piece by piece and answer all of your questions. So the first problem is asking you just to solve proportions. So make sure you have a good basis in solving proportions. Right? So we're going to just cross multiply whenever you have a fraction equaling a fraction, which is what we call proportion. We're just going to cross multiply. So I'm going to say x times x minus 3, which I'll write out undistributed so you can see what that looks like. And that's going to be equal to 3 times 18. 3 times 18 is equal to 54. So the first thing I need to do is to distribute the x, and I get that it's x squared minus 3x equals 54. Okay, and then to solve any problem that has a squared in it, or a quadratic problem, one of the biggest strategies to use, or the most prominent strategies, is to set it equal to 0. So I'm going to subtract the 54 over to the left and turn it into a trinomial. X squared minus 3x minus 54 is equal to 0. And I'm doing that because this is now a factorable expression. So we're looking for numbers that multiply to negative 54. The same numbers have to add up to negative 3. And in this case, I can say negative 9 and positive 6. Right, so I'm going to say these two values, when you multiply them, give me a 54. When I add them, give me a negative 3. And so if I set each of these equal to 0, x minus 9 equals 0 produces an answer of 9. And x equals 6, or x plus 6 produces an answer of negative 6. So I actually get two solutions here. And be careful, don't throw out at either of these answers, because this is not an application to geometry or an application to anything in real life. So these are both valid, good answers. Negative numbers are fine. It's only if we were to have to go back and plug that in and find out a side length or something that we might have to remove one of the answers. So those are both good answers, and we're going to leave them. I can do the same thing with problem number 2. This one's actually a little bit easier. When I do 2 times x plus 9, I get 2 times x plus 9, right? I can distribute this in a second. 8 times x minus 3, I'm going to do the same thing. And if you're comfortable distributing on this step, go right ahead. I'm just showing you kind of a little bit of the extra stuff that's involved. So I'm going to distribute 2x plus 18. And on the right-hand side, I'm going to distribute 8x minus 24. And then again, this is just a linear solve. So I'm going to subtract the 2x over to the right and make it turn into 6x. Okay. And then I'm going to add the 24 over to the left-hand side. So again, when I add, it looks like I get a 42. Okay. And then if I divide both sides by 6, I get that x is equal to 7. So in this case, just one solution, and that makes sense because it was a linear problem to solve. So we need to be able to solve any type of proportions, whether they are quadratic or linear. Okay, problem number 3. So this is where we're starting to get into similarity within right triangles. And so let me remind you what the two rules that we're about to use are. One of the rules said that the altitude is the geometric mean. So when we make that statement, the altitude is the geometric mean, we're claiming that in both of the mean spots of a proportion, which that's these two spots, I'm going to put the altitude. The altitude is the geometric mean of the segments of the hypotenuse, which I'm going to refer to as segment 1 and segment 2. Right? So what that means for our problem is that the altitude, which for us is this line right here, x, that this is the altitude. So I'm going to put that into the x. I'm sorry, into the altitude locations. I'll put an x there, of the two segments of the hypotenuse. So what that means is that this big hypotenuse right here, right, got split into two pieces. It got split into the 12 and it got split into the 6. Those are the segments that I'm referring to. The big hypotenuse got split into two segments, and so those values are going to go on the extreme spots. And now I just need to solve this. X times x is x squared, okay, and 12 times 6 is 72. Okay? And we always want to leave our answers, if we can, in simplest radical form. So when I square root both sides and get the square root of 72, I'm not going to leave it like that, because I can recognize that a factor of 72 is 36, and I like that because the square root of 36 is something that I know how to do. So I'm going to say the square root of 36 is 6 times the square root of 2, and I'm going to say this is the length of x, and that's where I'm going to leave it. Right? So to find y, I have options now. So I think we're going to do it using the other rule, just so you can see that in action. Okay, so the other rule says, let me get rid of the drawings all over my picture so we can start fresh again, is I'm going to say that a leg, right, so again I'm going to start here and say the leg is the geometric mean. So that whenever I say that something is a geometric mean, it's going to show up on both of the diagonals in the mean locations. Okay, and this is where you got to be careful. It is the mean of the hypotenuse, right, the hypotenuse of the big triangle. Okay, and then the other location is going to be the segment of the hypotenuse that is closer to that leg. And so here's what that means, just taking a look at our picture. If I am talking about this leg right here, the one that we're trying to find, if I go around the corner to the hypotenuse, it looks like I'm going to hit the 12. If instead, for example, maybe I had y over here, now I'm still talking about a leg, so I can still use this rule. But now when I go around the corner, I'm not going to hit the 12 anymore. The 6 is the closer one, right? So I can use this rule to solve for either of the two legs of the original triangle, right? But I always have to use the segment that is closer to that particular leg. So let's set this one up. So I'm going to call this one closer seg. So let's see if I can fit that in here. Closer segment, okay? So when I set this one up, I'm going to say, okay, the leg is the geometric mean. Well, for us, the leg is y, right? We don't know that one. So but in both of the leg spots, I'm going to put y. And it is the geometric mean of the entire hypotenuse of the big triangle, which for us, that's 12 plus 6. It's this entire length, 18. Okay, so 12 plus 6. And the closer segment we already said was 12. Right? So again, this is a solvable equation. I can do 12 times 18. Okay, 12 times 18 is equal to 216. So we're going to say that y squared is equal to 216. All right, and then again, we got to look for perfect squares in this one. I believe the biggest perfect square in 216 is a 36. If you do 216 divided by 36, you get a 6. Right? So I'm going to say that y is equal to the square root of 216. But I'm not going to leave it like that because this is really 36 times 6. And again, I know what the square root of 36 is, so I'm going to say that y is equal to 6 root 6, right? So again, this is using the two different rules, one that allows us to find the altitude or use the altitude, and the other one that allows us to use the leg or find the leg if we do know the other parts of it, okay? So just as a side note, this is just another strategy. If you forget these rules, which it happens sometimes where you get to the test and you're thinking about it and you can't remember the rule, remember that the Pythagorean Theorem is always an option. If you know two sides of a right triangle, you can use the Pythagorean Theorem to find the third. So if I focus again on this triangle, right, the little left-hand one that contains y, y is not only the leg of the big triangle, y is also the hypotenuse of this smaller one. So I could use the Pythagorean Theorem if I knew both of the legs of this smaller triangle. Well, guess what? Now I do, right? I know 12, and we just calculated, here it is, what x is equal to. So I could use those two values in the Pythagorean Theorem and use that to find y as well. So it's a different strategy, a different type of work to get to your answer, but it will get you to the same place, okay? So problem number 4 is just asking a very simple question. It's saying, what is the geometric mean of 9 and 16? So remember, the definition for geometric mean is or the application to find the geometric mean is to say the geometric mean is going to be that repeated value in the mean location. It shows up in both mean locations, the same value. Since they're saying what is the geometric mean, we're claiming we don't know what that is, so that's why we put x's in both of these spots. But we know that the other values that we're finding the geometric mean of, right, are 9 and 16. So again, 9 times 16 is equal to 144, which is really nice for us because x times x is x squared equals 144. Okay? And if I square root both sides, I get that x is equal to 12. So the geometric mean of 9 and 16 is 12. Okay? So now let's go to 5, 6, 7, 8, 9, 10. So this one's all using just this idea of similarity where we're saying here's a similarity statement. Okay? We're going to use the similarity statement to answer all these questions. It's giving us some information. It's claiming that these are similar. Okay? So I'm going to highlight my similarity statement so I can keep referring to it. And it's asking us to write about, first, the scale factor. So what is the scale factor of PQR to DEF? So remember, scale factors are a ratio, which could be written as a fraction, like A over B, or it could be written in its kind of A to B colon notation. So either of these would be an acceptable way to write this answer. But in order to answer their question, we need to find a corresponding side from each of these triangles that we already know the values for. Like, we're not trying to find them. They're not missing. We already know what they are. So if I take a look at this, right, if I'm kind of comparing these, I'm saying, well, I know everything on the left-hand triangle, but I only know one of them on the right-hand triangle. I only know what DF is. So if you take a look at here, at this similarity statement, D is the first letter and F is the last letter. So what we're going to know is that that side, DF, is going to correspond with the same two positions in the other similarity statement, the P and the Q. So if we set up PQ, well, PQ from the first triangle is 20, there it is, right? And then if I go to my other triangle, DF is 24, and then I can simplify this if I want to. 20 and 24 both have a 4 in them, right? So if I divide them both by 4, I find out that my scale factor is 5 over 6, right? So we can just find sides corresponding sides in both of these shapes, and we can set up a fraction, and then the reduced version or unreduced version, but the reduced version is usually the way we keep it, will be the answer. Okay, so now we're just going to answer some other questions. Now that we know the scale factor, it's going to end up helping us out with 9 and 10 later, but let's just answer some questions about the angles. So here's what's true about the angles in similar shapes. In any similar shapes, or any similar polygons, okay, corresponding angles are equal to each other. They're congruent, right? And again, I can take a look at my similarity statement, and I can figure out what corresponds with angle D just by looking at the statement. In this case, because angle D is in the first location, angle P is in the first location, those are corresponding sides. So I'm going to look at this and say, okay, angle D is equal to, and they're wondering how many degrees. Well, I'm going to look over here and say, oh, wait a second, I don't know anything about angle D, and I don't know anything about angle P, so I can't just swap them and say that they're the same. So we're going to kind of put a pause button on this one. We're going to come back to it. So I'm going to write pause here. We're going to come back and do that one in a second. So let's move on to the next one and see if maybe can we figure out that one instead. So R is the middle letter, and E is the middle letter. So if I come over here, I'm saying, okay, R. In this one, wait a second here, I do know about this one. It's 35. So I can say R has to be the same as E. They're equal to each other, so this is equal to 35. So that means I can fill in a 35 here. Okay. And now if you take a look at it, I have the ability to find P, which we didn't know what that was before. So let's go back and figure that out. We know that in triangles, they all add up to 180 degrees. So I'm going to say 180, and I'm going to subtract off the two angles that I have, the 35 and the 89, and I find out that this angle has to be 56 degrees. If P is 56 degrees, that means that D is also 56 degrees. So let's unpause problem number 6. And go back and say, now we know that this one's 56 degrees. And we can also fill in number 8 because that actually asks, what's angle P? Which, well, it's 56 degrees. Right? So I can fill in all that information using the swapping information in between the two triangles. Okay? So now let's find DE and FE. So DE and FE are lines that are showing up in this right-hand triangle. And so what I'm going to do is I'm going to set up this scale factor. Remember, the claim for similarity is that scale factor, that every single fraction, every single corresponding sides in a fraction should be equal to the same scale factor all the time. Our scale factor that we figured out is 5 over 6. So I'm going to say for number 9, 5 over 6 is what I want this to be equal to. Let me write my 5s like they're supposed to look. Okay, 5 over 6 is equal to, I'd like to find DE. Well, let's see, DE is out of the right-hand triangle, and that was our 6, right? So I'm going to put that on the bottom, say I don't know what that is. And now we need to see what goes with DE. Well, if you notice, again, DE is the first two letters, PR is also the first two letters, right? So if I take a look at PR, it's worth 40, okay? So this looks like the equation that I need to solve. That if I cross multiply this one, I'm going to find out that 5x is equal to 240, right? And that means that it looks like x has to be equal to, if I divide both sides by 5, I believe this comes out to be 48. Okay, so that means that DE, okay, is 48 long. So I can come over here and add that to my picture. Okay, and then FE, I'm actually going to do the exact same thing. FE's ratio still needs to be 5 to 6. So I'm going to say 5 over 6. Right, and again, I'm going to take a look and I'm going to say FE, right, FE is also out of the right-hand triangle, so that's the bigger number. The 6 came from the bigger triangle, so that's my x. And then 5, what goes with FE? Well, that's the last two letters, so in this case, RQ is the last two letters, so I'm going to put a 36 up here. So I need to solve this one. This one's not as straightforward when you're doing your problem. You're going to end up with a decimal, but I'm going to say that 5x is equal to 36 times 6, which I believe is 216, okay, 216. And then when I divide both sides by 5 to figure out how long that side is, I find out that it's 43.2. So in this case, this is 43.2 units long, right? So we used proportions. That 5-6 ratio should apply to all of the proportional sides, or all of the sides in a ratio for this fraction. So we use that information to help us figure it out. So I'm going to stop this video. I'm going to finish up the problems in the next video. The 11 through 20 to finish up our discussion about similarity.